All right, good afternoon, everyone. Can you guys see my screen?
Yes, sir.
All right, great. So we're gonna do a revision of last week because remember we want to be 100% clear on topic of programming. So one simple question: um, How would you describe an algorithm? How would you describe an algorithm? Simple question. Anyone?
Sir, procedure used to solving problem.
A process used to solve a problem. Good. Anybody else want to try? Anybody else want to add?
Or it could be like a set of instructions.
Mm-hmm. Good. So a process, a set of instructions, a series of steps, however you want to describe it. But the end goal is that a algorithm takes you from a problem to a solution. Always got to remember that. An algorithm takes you from a problem to a solution. Good. So that's mainly what we would have covered last week. What is an algorithm? Then we looked at what is the algorithm phase. When we are creating an algorithm, what we have to go through, you basically have to define the problem, explain what is the problem, what caused the problem, what are the effects of the problem, propose your solutions, evaluate each one, look at the advantages and disadvantages, then pick which one is the most reasonable, design an algorithm for that solution, and then test that algorithm. After finish testing it and it's correct, then we create a program. And then we run the program and maintain that program. So that's a summary of what we would have covered last week. Now, before you actually create an algorithm, so we're gonna move past these first three steps and jump to designing the algorithm. Step number 4. But before we actually do step number 4, there is a step 3.5. We can see it. Before you design the algorithm, you should do something, and that is create what is called an IPO chart. And the IPO is basically input output processing chart. Now, what is the IPO chart? Well, IPO charts are used to identify the input for the algorithm or the program. So, the information you're going to need to solve the problem. So, say for instance, the problem is that you don't know how to calculate a number, you don't know how to do division, maybe it's a lengthy division, then the input is going to be the numbers to carry out the division. The P, the processing, you have to identify what is the processing. How are you going to convert the inputted data into the desired output? How are you going to calculate that input or manipulate that input to change it so that you can get that particular output? And then lastly, for that chart, you have to document um, the output, which is the goal of the problem. What is the result? What do you want from this um, program here, basically, this algorithm? What should be the output? Now, an IPO chart is not actually a chart. It does call it a chart, but it's actually a table. So whoever created it in the beginning called it an IPO chart, but it is not a chart. It's a 3-column table, one for each letter, input, output, processing. Each column represents the 3 components, input, output, processing. The storage component is not usually documented. So that's why it's not the IPOS chart. It's the same cycle that we talked about last week, and we learned in third form, but just that the storage is not that necessary for us to document. We could document it, but it's not that necessary. So we only focus on what is the input, output, and processing. So once again, IPO chart is simply a table that we use to document all of the input, all of the processing, and all of the output. And by documenting it in this table, we can simply have all the necessary information when we have to create the algorithm. We're going to know, because in the algorithm, you have to specify what is the input, what is the processing, what is the output, how all of these things are going to be carried out. So by having that table in like an overview manner, you'll be able to know what to put in your algorithm. So let's look at an example. You're given a problem of finding the sum of three numbers. So that's the problem. We want to know what is the sum of three numbers. What is our goal or output? What input information do you have? So the output or goal is a number, which is the sum of the three numbers. So that's our output, the result of the addition of the three numbers. The input is made up of the values of those three numbers that we want to add. So what steps are needed to convert the input into the output? That is going to be our processing now. So the addition, turning that three numbers into the final output, is our processing. So how do we document that? Well, the input of the three numbers, adding the three numbers, output the sum of the numbers. So this is the actual table here. So I'm just going to draw in the lines so that you can see it's an actual table, three-column table. You have the input column, the processing column, and the output column. Now, later on, we're going to learn about how we store data. That's going to be in the next chapter. But for now, where you see number 1, number 2, number 3, those are basically what is going to store the three values. So the first number is going to be stored into number 1. The second number is going to be stored into number 2. The third number is going to be stored into number 3. So notice we have as input 3 numbers. Now the next step is processing, and you could write the calculation. We're going to see that later on. You can actually write the formula, or you can write it in a sentence format, in a descriptive format, whereby it says add the three numbers together. That's simple. And then the output is the result of that addition. So it's that simple. The IPO chart, 3 columns, documenting what should be inputted into the algorithm, these 3 numbers here, what should be processed, what should be calculated, what should be manipulated, and what should be the output from that program or algorithm. Think you guys clear on that?
Yes, sir.
All right. Should be relatively straightforward. So you can follow an IPO chart by reading each column from left to right. For example, the input column indicates, so the input column indicates that you input 3 values, as I mentioned. In the processing column, you add the values that were input, and in the third column, it outputs the results of the addition, as mentioned. Let's look at another example. You're given the problem of finding the average temperature. And simple maths. We should know what is the calculation for average? You add everything together and you divide it by how many items there are. So we're going to be looking at the maximum and minimum temperature, and that will give us our average. And the simple calculation is to add the max and the minimum and divide it by 2 because it's only 2 items, right? So we have our table and our input. It's only 2 values, the maximum temperature and the minimum temperature. Now our processing, what are we going to do with this max temperature and this minimum temperature? Well, we're going to calculate what calculation are we going to carry out? Notice we are now creating the formula. We're saying to add max and min temperature, and notice the bracket, simple maths. Whatever's in bracket, we calculate first, and then we divide it by 2. So we have our calculation there. Now, what should we output? The average temperature. So we input 2 values, we have our calculation going on here, and then we have the output of that result, the average temperature. Are you guys clear in this example?
Yes, sir.
Stephanie and Amelina, you guys following?
Yes, sir.
Okay. The third example, we're going to read a number, so it's going to be a random number, add 10% to that number, and then output the results. So we take a number, add 10%. So you can think about it like if we have to add 10% to a price of an item. So we input a number, any random number, and the processing, what are we going to calculate? What are we going to do? Now, in programming, we usually carry out, if you notice, let's look at the output result first, the output column first. Notice it says output result. Well, this here is basically a container. We're going to learn later on, this is called a variable. It is what is being used to store the value. That's like how the word number here is used to represent that we're going to put in a number. That is what is storing the number also. So as we can see the word result in the output column, notice you can also see that word result in the processing column. So this is another method of writing your calculation. With this method, we carry out the calculation that is on the right hand and then store it into what is on the left hand. That's what is meant here. So on the right hand of the equal sign, that's what I'm referring to, the right hand side of the equal sign. We take number, but remember we have a bracket here. So we have to say number multiplied by 0.10, which is roughly going to give us 10%. And then we add that back to number. So that is taking that number, calculating 10% of it, and then adding it, that 10% to that number. And then we store it into this variable, this container called result. So that is why in the output column, when it says the output result, you're basically outputting whatever would have been resulted from this calculation here. Or the other form of calculation is that we take that number and we multiply it by 110% basically, and then we store it into that result variable once again, and we output it. So if you notice, it's basically simple maths we're doing right now to carry out our calculation. So what you would have learned in maths is going to play an important role in programming, because you need to remember those rules that you would have learned so that you can apply it. All right, are you guys clear on this example here? Any issues with it?
No, sir.
All right. Final example. Input the regular price of an item, calculate the discount amount of 20% of that regular price, and also the discounted price. So we need to calculate what's 20% and what is the actual price, and then output the discount amount and the discount price. So we actually running a business here now. So if you notice, if you have a business, you can actually create a program to do certain calculations for you. So in this program, we input the regular price. So say for instance, the item is $200. We put in $200. Now we need to calculate two things: the discount amount, how much is 20% of this 200, and what is the discounted price now of that item. So I'm just going to draw a line here because this is two different calculations going on here. So the first one here, remember we work from the right hand side of the equal sign. So the regular price, which is $200, we're going to multiply it by 0.20, which is basically going to give us 20% of 200. And we store that into the variable discount amount. So if we notice in the output, we're outputting discount amount. So we take in the price, we calculate that 20% of that regular price, and then we output how much is that 20%. The next calculation, once again, on the right hand side of the equal sign, we're going to take the regular price, that 200, and subtract it from the discount amount, which you would have calculated above here. So 20% of 200, whatever that may be, that would be subtracted from the 200 and then stored into discount price. And then we output what is in that discount price here. Are we clear in this one?
Yes, sir.
Yes, sir.
All right. Give me a second. I am looking for. All right. So you guys are going to create your own IPO chart now. I want to see what you're going to come up with. So create an IPO chart for the following. Um, let's keep it simple for now. Um, let's see. Mm, all right. The total price of 3 items. So create an IPO chart to get the total price of 3 items. So you go to the supermarket, you go to the shop, you bought 3 items, create an IPO chart to, to get the total of those three items. Send me a picture in the group when you're finished so that I can see what you have. If you have any questions, you can let me know.
Names of the items, or you could just say like item one, item two.
You can do that. Item one, item two. It can be any item, so you don't want to be specific. But that's a good question. And this is something you can keep in mind for the future. In a case like this here, when we're creating a program, the program possibly could be used for any scenario. Like in this case here, if we're totaling the price of three items, it could be any three items. Any three item from a supermarket, from a hardware store, a grocery store, anywhere. So sometimes when we're creating the program, we create it in a general manner so that it could work for like any case instead of being something specific, unless we have to be specific. So that's something you can keep in mind. All right, so we have two IPO charts. We're gonna try today. So the first one, you accept the price of three items, and then you calculate and display the total. And then the last one, read the name and age of a person and calculate and display the age in years. So we're only focusing on the years, nothing too technical.
For the first one, you gotta put the actual price.
No. Mm-mm. Remember we talked about um, having a container to store the value in. So you just make up a container, like how we have in this case here, number one, number two, number three. So that's a container to hold that value. Good afternoon, Africa. We're currently creating IPO charts. Do you know what is an IPO chart?
Didn't we discuss this last week?
No.
Oh, it was just the cycle last week.
Mm-hmm. Yeah, do you know what is an IPO chart? Do you know what is this here?
Yes, sir.
All right. Well, can you explain to me what is an IPO chart?
So it takes the three different stages of the process and it separates it to show you the, I wouldn't say progress. What would I say? The like steps of getting it done.
Okay, seems you have an idea. So it basically documents the input, processing, output stages of the algorithm. That's why it's called IPO. So, like in this example here, it is to calculate three numbers. So the input of that algorithm is putting in three numbers, number one, number two, number three. The processing is the addition of those three numbers. So how we turn in the input into the output, that's the processing. And the output is what we want to be displayed from that algorithm. So that's going to be the result of that addition. So it's just these steps we are basically taking. So I would have mentioned that it's basically, we can consider it as step 3.5 because it's something you do before you design an algorithm. So with that in mind, we have an activity right now. You can ask me any questions you want. The activity is to create the following IPO chart. So can you start that?
Yes, sir.
All right. Amelina disappeared. All right. Total price item. Very good, very good. Stephanie could have sent it in the group so everybody can see your example. But you have the right idea and it is correct. Send it in the group, yeah, so that the others can see. Yeah, that is correct. You can work on the other. Um, Shucks. Oceanic, you need to send it back. Don't do the one-time image because we want the others to see and learn from it. Okay, price of item one, two, three. Why looks so similar to
Wait, no, sir.
Mine. That's not mine.
I'll be wondering there. Okay, item one cost, good. Item one cost plus item two cost, total cost, total cost. Very good, very good. You have the right idea. You can start working on the second one.
We're supposed to add in the underscore.
Um, Later on, we're going to learn. It's the same as we would have learned in database. Certain names, we certain things that we're naming, we are not supposed to have space in it. But in this case, we're still learning. But yes, the answer to the question, you either add in underscore or no space. Lenny getting through?
Yes, sir.
All right. All right. Item one, two, three. Add item one, two, three. Total cost. Good. Um, Only thing you had total price and then you jump to total cost. That's the only issue. Item one price, item two price, item three price. Good. Very good, Africo. Good. All of you.
Sir, was it the price?
Oh,
What gonna happen?
with what I just said earlier.
Yeah.
All right. So, remember I said that the variable, what is being used to store the value, that's what you're naming right now. So um, that's the total price, the total cost, and the item price one, price two, and so on. So if you use a different name, it won't. It's like if you're calling on something else. That's like how each of us have different names. It's like you're calling on somebody else. You're telling it to look somewhere else for the value. So it won't get the correct value, even though it sounds similar. Remember, in a computer doesn't think like how we think. It might sound similar to the computer, but once it's spelled different, it's something totally different, even if it's just one letter. All right, congratulations. Everybody finished the first one, so you can work on the second one.
Sir, you can explain back the second one?
All right, so the second one, it says to read the name. Read is a keyword. Um, I don't think we looked at keywords as yet. No, we didn't look at keywords as yet. Read is a keyword to indicate input. Is another word that can be used to instead of the word input. So it's like I'm saying input the name, read the name of the person and their age. So you're going to accept the person's age, you're going to accept the person's name, and then you're going to calculate what is the age of the person and then display that person's age. Hold on. I just realized because it's telling you to. Hmm.
Sir, if you put the present age, how are you going to
Yeah,
calculate it?
yeah. I just realized that, so I need to check.
Sir, wait. Did you mean days of birth?
Yeah, but I only want to focus on the year. I want to keep the calculation simple. So read the name and birth year of a person. So hopefully this clarifies it. So read the name and birth year of a person, calculate the age, and display their name and age in years. All right, let me know if you're clear on it now. Read the name and birth year of a person, calculate the age, and display their name and age in years. We want to know the exact age. You just want to know like, the age in years.
So we can input any name, right?
Yeah, any name. But remember, just like the price, it's not a specific price. So similarly, the name is a general name. Any person should be able to put in their name. Mm-hmm. The person. Good. Age. Good. All right. Stephanie, the only thing is under the processing, you're gonna take out insert name of person. Because remember, there's a input, and input should only be under the input column.
So in the processing part, you're only focusing on the age.
Yeah. So processing is only about calculation. It's only about how you're manipulating what would have already been inputted.
But still leave name in output.
Yeah, because remember, you have to indicate what you're outputting. So if you didn't mention name on the output, it's like if you're not outputting name. So you have to put it under there. All right. No, Amelina. Current year,
Oh,
age. Um, look back at the example of when you were calculating the price. Remember, you weren't um, focusing on a particular price. You didn't you didn't put under the input 200, 300, 400. You put a container to store that three different price. So similarly, under the input, you need a container to store the name, not just put a specific name. And same for the age also. Whenever we're doing programming, the person has to put the information into the program. In some cases, it will already be in the program if that is required. But in most cases, it's for somebody to type it in. So you as the programmer now, you have to set it up in such a way that it's going to accept what the person types into the program. So you got to create a variable, a container, to store the person's name, to store the person's birth year, and then you calculate that age and you output the person's name and that age. Good. Name of person, age of person. We're gonna be focusing on the year, but you have the idea. So current year minus year born, you get the person's age. Good, good. So that one there is better. All right. So it's just Africa and Oceania. All right. Africa sent hers. Person, date of birth, age and year, current year minus that. All right. Africa, you then output the name, the person's name. You output their age. Yeah. Um, Oceana, name, birth year. Age is going to equal current year minus birth year. And name and age. Okay. Oceana's one is perfect overall. Just all of you did good. You did well in yours. Um, but why I'm saying hers is perfect overall because some of you made some slight changes when you're using the container names, the variable names. You use one name in the input, then you use a different name in the output, and so on. But like I said, we're not focusing on that. We're just focusing on the idea that you understand how to document the input, how to document the processing, and how to document the output. But all of you did well in your two activities here. Any questions on them before we move on? The next chapter um, is going to highlight some additional points that we need to take into consideration. So when we do cover this chapter here, then we're going to go back to another example, working on another example of an IPO chart to ensure we fully perfect it, following all of the rules and so on about naming and variables and so on. But for now, it's just having the understanding. The IPO chart documents all the input, the processing, and the output. All right, if no questions, we are going to start chapter 9.2. We're now getting into designing an algorithm. So we have an idea how to create an IPO chart, but we need to know how to design this algorithm now, how to convert, this IPO chart into an algorithm. So let me begin the reading. So to help with simplification and development of the programming problem, algorithms can be created as pseudocode or flowcharts. So if you guys can remember in the very first class, I would have created an algorithm for you. I would have um, typed something like this here. Um, I said problem, and then step one. How did I do that? Why are you doing that? So problem, I am hungry and technology can be so stupid at times. All right, so and then I said we can go to the supermarket, buy ingredients, things like that. We would have discussed in the last class. So an algorithm is more of a descriptive manner of writing your steps. It's more descriptive. You can write it in plain words. What exactly is going to happen? So, for instance, you can say add the numbers, um, add the number, or you can say add the first number to the second number, and that could be a description, because otherwise the equivalent of that would have been um, number 1 plus number 2, which is step 3 and 4 is roughly the same thing, doing the same thing. But what I'm trying to explain is an algorithm, the steps are a bit more descriptive. You can write it in a sentence format describing what exactly is the action. Now, as we read here in this paragraph, we can represent our algorithm or create an algorithm as the following, either a pseudocode or flowcharts. So these are two other methods or two different ways of representing the algorithm. Think of it that way. And these here actually have rules that you must follow. They have guidelines that you must follow. So it's not like the algorithm whereby, yes, you're going to write it in a logical manner, but you're allowed to be descriptive in what you're describing each step as occurring. But the pseudocode and the flowchart, they represent those steps differently. They might structure it differently, and they have certain rules and keywords and statements that you must use in order to create it properly. So, with that in mind, let's continue, and we're gonna look and we're gonna see what's the difference between a pseudocode and a flowchart. So, an algorithm, as we would have already learned, is a set of step-by-step instructions that is required to obtain the solution to a problem. So remember, algorithm always leads from a problem to a solution, and it's simply the steps that we take. Now, it must have a set of rules, it must be explicit, and it must have a clear stopping point. So it must be to the point, basically. It must be clear, it must be specific, it must be following these rules, so that if anyone is looking at it, reading it, they will be able to understand exactly what is happening. Now, it is really used to expand the processing part of the IPO charts. So that's why we were learning about the IPO chart. And this is the important part here. Using diagrams for flowcharts. So using diagrams for flowcharts. So this is how a flowchart is different from a algorithm. It's the same series of steps, but the flowchart uses diagrams to represent those steps. Whereas the pseudocode uses English type statements to represent those steps. So let me find an example so that I can show you guys. Pseudocode versus flowchart. Good. So this here, shucks, it's a video. All right. So this here is an example of a algorithm pseudocode on the left hand side versus a flowchart on the right hand side, and they're roughly doing the same thing, but just that one is in English sentences, as you can see in the left hand, and one is in diagrams, shapes, basically. Um, where is my pencil? Edit the image. Yeah. Mhm. I just wanted a pencil. Either way. So find the sum of five numbers. We're adding five numbers. So algorithm is simple English. Step number one, initialize sum equals 0 and count equals 0. So notice it's a bit more of, like, if you're, it has a more of a structure. It's not like how we were writing, go to the supermarket, add the first number to the second number. It doesn't say um, put 0 into sum or something like that. It has a more of a structure, as you can see here. So it's saying initialize sum equals 0. Wherein, if we look at the flow chart, notice it has the same step, but in a shape. Sum equals 0, count equals 0. And then step number 2, enter n. Notice that is in a different shape. And then we have find sum plus n and assign it to sum, and then increment count by 1. And then in the rectangle here, sum equals sum plus n, count equal count plus 1. Don't worry if it all sounds technical. All I'm just showing you right now is that a pseudocode and an algorithm, remember I said a pseudocode and a flowchart, they're just ways of representing the algorithm. They're different methods of representing the algorithm. The algorithm is more of writing it plain in English, writing it more descriptive. Whereas a pseudocode is kind of the same thing. You're writing it in English words, but it's going to have a bit more of a rule, you can say, a bit more of a guideline. Like you can see in this example here, um, it's a bit more structured than the descriptive manner that I was writing in. And the flowchart, as I said, uses diagrams, as you can see here. So just that you need to take note of for now. Pseudocode and algorithm both use English type statements, and only the flowchart uses diagrams. Are we clear on that? Are we clear?
Yes, sir.
Any questions from anybody? Anything you want to clarify? All right, no questions. Good. So let me turn back color to blue. Now,
Like different layouts of flowcharts.
what was the question?
Different layouts of flowcharts.
What do you mean different layouts? I don't think I hear the full question.
Do you have like different layouts of the flowchart? Like
Um,
how it went from top to bottom, like vertical,
you
and then some went horizontal.
To answer your question, we usually go top to bottom because that's how we want to represent the flow of data, starting from the top going to the bottom. And then if you notice, these lines would indicate how the data would flow. There's a whole chapter in flowchart that we're going to go into detail later on. But the lines indicate how we go through from one step to the next. And we usually go top to bottom. The only time we go sideways, horizontal, is as you can see in this case here, if we need to loop back up, if we need to go back to a previous step, and if we need to take different paths, if it gets like really complicated, the flowchart gets really complicated, and we have to go back to certain steps and there's different parts and so on, then we go horizontal. But in most cases, we're going vertical, up and down. Well, mostly starting from the top, going down. And it's the same pattern also for the algorithm. If you notice, step one, step two, step three, step four, we're technically starting from the top, going to the bottom. But just that the diagrams, we can see it more in a pictorial manner. Any other questions? So there is no,
Excuse me, sir.
yeah,
I saw that there was different shapes at the parts. Is there any meaning to that?
yeah. We're gonna learn later on that each shape has a meaning. When we get to flowcharts, we'll learn about all of that. One has a meaning for indicating inputs, one has a meaning for output, one has a meaning for calculation, and so on. So the shape tells you what action is to be carried out. If you want
Okay,
to,
sir.
if you want to read ahead, that's it's already in your classroom. Um, that is chapter 9.4, and you can see all the shapes and what each one means. Well, we're going to look at that all later on. Yeah, so there is no one specific layout to the flowchart. It's just based upon how the steps needs to be carried out, basically. That will determine how you're going to draw it. All right, so next, the algorithm should start with a title and end with the keyword end, because we need to indicate where the algorithm is starting from and where it is ending. So whether it's the algorithm, whether it's the pseudocode, whether it's the flowchart, it must have a clear starting point and it must have a clear ending point. So as you can see with the flowchart, there's a clear keyword that says start, and there's a clear keyword that says stop. So it's a clear indication the flowchart starts from here and ends here. So it can either be start or begin, either one, or it can be stop or end, whichever one. They both basically mean the same thing. Even for the algorithm, well, notice it mentions here the algorithm must start with a title. That title is an indication of the starting point. But if you want to put the keyword start or the keyword begin, nothing's wrong. You can do that also. But having that title indicates the start of the algorithm. So, um, like how you have the word algorithm here, just imagine that was the title, and that's an indication that this is the start of the algorithm. So, um, so the first thing we learned here, actually the first thing is at the top here, that an algorithm can be represented either by a pseudocode or a flowchart. The second thing is that you must follow the rules when it comes to developing either the algorithm, the pseudocode, or the flowchart. The third thing we learned is that a flowchart uses diagrams, whereas pseudocode and algorithm uses English type statements. And then the fourth point we just looked at, it must have a clear starting point and it must have a clear ending point. Any questions? All right, let's move on. Now, developing a program can be a major undertaking, So, good algorithm design is very important. It is not always possible to satisfy all the requirements of a good algorithm completely at the same time. Some problems may be complex and hence require complex solutions. However, there are some general goals in designing algorithms. A good algorithm should be the following. In a nutshell, you want your algorithm to be perfect. But obviously, we cannot make it perfect. That's probably impossible for us to make it perfect in the first go. So we try our best to make it as perfect as we can. And we do that by ensuring we have good algorithm design. Now, the following are some characteristics of good algorithm design. So we have being correct, being simple, clear, precise, easy to implement, and efficient. Those are one, two, three, six characteristics of a good algorithm. What makes a good algorithm? So the first one, how do we ensure that the algorithm is correct? Well, an algorithm should accept all inputs, even invalid inputs, and output a correct answer or meaningful response or message. Anybody understand anything from that? What do you think that means? It should accept all input, even if it's invalid, and give you the correct answer or a meaningful message. What is meant by that? Any idea? None? All right. Um, let's see. All right, that's not working. Mm, all right, let me use the same calculator. I was checking to see if it's going to do what I wanted to do, but it didn't. This calculator here, it was designed to calculate numbers. So obviously, if I type in a number, it's going to accept that number. But if I start typing a letter, if I start typing a letter, um, should it accept those letters? Should the calculator accept those letters? It's a simple question. Should a calculator accept letters?
No, sir.
No, because we don't calculate letters. So it should not accept letters. So what I'm getting at is that an algorithm, it should accept all inputs. What is correct and what is not correct. What it should accept and what it should not accept. It should accept everything. So, for instance, this calculator here, it was designed to add numbers. So it's going to take in numbers. But at the same time, it was not designed to calculate letters. It wasn't designed to add A plus A or B multiplied by C. It wasn't designed to do that. But it should still accept it. It should still accept that letter. But when it does accept that letter, it's not that it's going to give you a correct answer, but that it's going to give you a meaningful response. It should tell you that, look, I am a calculator and I cannot accept letters. It should tell you what is the problem and that you're basically the problem. That I can't calculate letters, so why are you typing letters? You know, sometimes when we use a software or we're doing something, we get an error message that we cannot type something or we cannot press that key. Or even when we're working on a computer, sometimes when you press a button, we get a sound and nothing is happening. And the sound is an indication that it's not going to do anything, that we're not supposed to be pressing that button at that moment in time. That is it accepting the input. But at the same time, it's a wrong input and it's telling us that what we're doing is wrong. So some software, they do that. Um, like if you go and sign up for an account and you have to type in your name, you have to type in your address, you have to type in a number, and sometimes there's a number field, and you go and type in a letter, the system might pop up an error and tell you that, look, we cannot accept the letter because only numbers are supposed to be entered here. That is how we make an algorithm correct. It accepts the correct input and the incorrect input, and it's either going to give you the correct answer or it's going to tell you a meaningful message. It's going to say the what you would have typed is not correct. Please type the correct answer. Are you guys clear on that one?
Yes, sir.
Yes, sir.
All right. Now, so we're finished with correct. What about being simple? How is an algorithm simple? How can we keep it simple? Well, each step of the algorithm should perform one logical step in solving the problem. I would have told you guys about this when we were designing the algorithm. Each step should be a logical step. One small step, not a whole overview step. So, like if we just write make a sandwich, there's so much things that could go into making a sandwich. We gotta buy ingredients, we cut up ingredients, um, we gotta prepare the ingredients. There's so much things that can go. That step could be subdivided into. And so that's what we mean. Each step must be one small logical step, one small thing that we're doing. So if we say um, wash the onion, can't get um, smaller than that unless before you can say turn on the pipe and then you wash the onion. So that's where we're getting at. It must be simple. One logical step. Each step must be clear, a clear action as to what to be carried out. The third characteristic, you must be clear. The algorithm should be easy to read and understand. So that relates back to being simple. When a person reads the step, it should be no confusion as to what we should do. If it says wash the onion, we shouldn't be wondering how we need to wash the onion. So that means we should have said how to wash the onion. We need to peel off the skin before we go and wash it. Or we're going to wash it with the skin on because we want to wash the dirt off. So you need to be clear what the person is actually doing. They're washing it with the skin on or they're washing it without the skin. 4, we need to be precise. The algorithm should present the solution steps precisely and concisely without referring to low-level code, programming code. So, precise steps, once again, they're going in order. Step number 1, 2, 3, 4. It must be logical. That's the first thing we need to take into consideration. The steps must be logical, in the logical order. So you can't say fry the onion and then you can say peel the onion. It must be in the logical order. And the last part of this being precise, it says that we should not refer to low level code. This is something we're going to learn later on. Um, but low level code, does anybody know what's low level code or programming code?
Yes, sir.
What is it?
Based on my understanding, it's code from low level languages like C that were created in the earlier days.
And what format was C written in?
Should I explain this? I can't really explain it, sir.
All right. All right. So there's different levels. I hope you guys can see that. See the image?
Yes, sir.
All right. So there are different levels of programming languages. Let's see if we can find a clear image. Mm. All right. I'm not finding the image in a better quality, but just note that there are different levels of programming language. We have what is called the high level language, and we have what is called the low level language. Now, simply to make it as simple as possible, high level languages are languages that we can read and understand. It's like if how we can read and understand English. So the programming languages are written in English basically, such as Python, C++, Java, and so on. They are written using English words. Now, low level language refers to assembly language or machine code. And we as humans, especially the machine code, do not understand it. Why? Because, notice the example here, it is binary numbers. So, everything that the computer does, everything that the computer sees, every way that the computer operates, it's all being done in binary. Even even though what you're seeing on the screen right now, all of these fancy things that you're seeing right now, all the computer is seeing is ones and zeros because the computer only sees in machine code. It only sees in low level language, that binary language. So low level is referring to binary. So that's what is meant by being precise. We shouldn't refer to any of those low level codes. We shouldn't be mentioning anything about binary or any binary combination or so on. We want to put it in such a way that as humans, we should be able to read it simply and be able to understand it. That's the goal of algorithms. Anyone should be able to read it and understand it. Now, how is an algorithm easy to implement? How can we make it easy to implement? Well, the algorithm should be relatively easy to translate into the programming language. And that's why we create an algorithm. Because all you have to do is translate it now over into whatever programming language that we want. So let me give you an example. Each of you should be studying a foreign language. Now, in most cases, you might have some sort of activity while studying that foreign language to write an essay, write a paragraph, write some sort of description. And they're going to tell you write it in that foreign language, French, Portuguese, Spanish, whatever the case may be. Now, tell me which is going to make it the task easier on you. Option one, write the paragraph or the essay only in the foreign language, whether that is French, Portuguese, Spanish. You write it only in that foreign language. Option one. Or option two, you write it in English, how you understand it, how you want it to be structured, and then you translate it now into that foreign language, whether that's French, Portuguese, Spanish, which would make that assignment easier. Option one or option two? Like you're creating an option three.
No, sir. I was going to say option one.
Option one, why option one?
I think both. All right. So for option one, certain things can't exact. Certain things that are in English, they won't be translated the same way in French, or like
Mm-hmm.
French has a different way of expressing themselves. So how you would think in English, it would, or maybe you have a higher capacity in English, so there's certain things that you won't know to write in French.
Mm-hmm.
So it doesn't make sense to write that well in English and then you can't translate it properly in French.
Mm-hmm.
And for the second option, why I'm also choosing that is because when you understand what you know, you could write that down and write it over as long as you make it simple.
Mm-hmm. Good. I've given this same question. So I've used the same question while teaching program throughout the years, and I've gotten the same response. Persons would choose would have a balanced answer between the two, mainly because they say that writing directly into the language is much easier because of the same reason. But at the same time, when you think about it, if you don't have a plan as to what you're going to write in that foreign language, it's going to make it a bit more difficult. So that's why I asked the question, which is going to make it easier for you to create that essay in that foreign language. So in most cases, having the idea already in English and then you doing your necessary conversion, translation, whether you got to change up the idea, but the main um, idea basically is that having something to relate to as a guide as to how you're going to create something can make the task easier. Because even if you don't write that essay in English, you're still thinking about it mentally, what to write. So you're actually preparing it in your mind, even though you might not be writing it in English. You're actually preparing it in your head. You're thinking about it first in English and then you translate it. So it's still the same concept. When we are creating a program, the algorithm must be designed in such a way that it's easy for us to translate into our programming language. Well, unlike actual language translation, which can be different, programming is much more easier because you don't have to worry about one thing having a different meaning than the other. Whatever you write in English, that exact thing can be carried out in that programming language. If you say add 1 plus 1, you know exactly how to do that in that programming language. If you say check what if one price is greater than the other, you know exactly how to do that in that programming language. So that's why, in the first place, the algorithm must be clear, must be precise, must be simple, so that when you're going to do your translation, now anybody should be able to look at it and convert it into whatever programming language they might choose. And then, lastly, how can we make our algorithm efficient? Well, the algorithm should enable the program code to produce results quickly, depending on the problem size, and not waste any memory or time. So we want the algorithm to work quickly, to do its job fast. And one of the ways that we can carry that out is by reducing the number of steps. So, say for instance, an algorithm has 100 steps. Yes, we've been learning that we need to make each step specific. It must be logical. It must be a small direct step. But at the same time, we want to not have too many steps. Because, say for instance, we have an algorithm with 100 steps, and then we have an algorithm with 1,000 steps. Which do you think would take longer to run?
The one with 1,000 steps.
Right, that's simple. The one with 1,000 steps. So, at the same time, you want to be simple, you want to be direct, specific, and so on, but you don't want too much steps in your algorithm. You don't want to make it too complicated. And there are certain techniques. It's not that you have to take out steps. There are certain techniques that you can carry out to reduce the number of steps. Because in some cases, you will have to get 1,000 steps. But there are certain techniques that we're going to learn later on that can allow you to reduce that 1,000 to maybe 900, 800, and lower. So we want to ensure our program algorithm is efficient by running quickly. Now, and then it shouldn't waste any memory or time and so on. So that's making it efficient, how it is storing the data and so on. All right,
Excuse me, sir.
go ahead.
Would one be like repeating a step that came before, like just saying refer to that one and repeat it?
Right, exactly. So, as you said, you have step number 5, and step number 5 is to do that. And you want to do the same thing again. Instead of you typing back that entire step, you tell the program, do back step number 5, and then continue from where. So that way you reduce that code. Good. So that was a simplified version of that. So, as we just looked at, we looked at the characteristics of a good algorithm. We said that it must be correct, simple, clear, precise, easy to implement, and efficient. Are you guys clear on all of them?
Yes, sir.
All right. All right, we are already at 3:30. So next week we're gonna look at variables and constants, and then wrap up this chapter here. So to review what we would have considered today, um, we reminded ourselves of the algorithm phase and the various steps, and we added a step to the algorithm phase, step 3.5, whereby we learned how to create IPO charts. Remember, it's not a chart, it's a 3-column table, and it's simply to document the input and the processing and the output for the algorithm. And then we looked at how we can create the algorithm. We can either create it as a pseudocode or we can create it as a flowchart. We looked at what's the difference between the two. One uses diagrams, one uses English statements. We said that they must have a starting point, they must have an ending point, and then we just looked at the characteristics that would make an algorithm good. All right, any questions before we close?
No questions, sir.
Any questions from anybody else?
No, sir.
All right. If no questions in today's class, that will be the end. Enjoy the rest of your day.
Same to you, sir. Bye.